algebra of events. Let A, B, C be events associated with an experiment whose sample space is S. 1. Complementary event. For every event A, there corresponds another event A dash, called the complementary event of A. It is also called the event not A. For example, take the experiment of tossing 3 coins. An associated sample space S is shown. Let A be the event when only one tail appears. For the outcome H, T, T, the event A has not occurred. We may say that the event not A has occurred. Thus, with every outcome which is not in A, we say that not A occurs. Thus, the complementary event not A to the event A is A dash, which contains HHH, HTT, THT, TTH and TTT. Or we can say A dash contains all the elements belonging to S and the elements which does not belong to A, that is S minus A. Number 2. The event A or B. When the sets A and B are two events associated with a sample space, then A union B is the event either A or B or both. This event A union B is also called A or B. Therefore, event A or B is equal to A union B, which contains the elements belonging to A or B. Number 3. The event A and B. If A and B are two events, then the set A intersection B denotes the event A and B. Thus, A intersection B contains only those elements which belong to both A and B. For example, in the experiment of throwing a die twice, let A be the event, score on the first throw is 6, and B be the event when the sum of two scores is at least 11. Then A and B contains the shown elements. Therefore, A intersection B contains 6, 5 and 6, 6. Number 4. The event A but not B. We know that A minus B is the set of all those elements which are in A but not in B. Therefore, the set A minus B may denote the event A but not B. It can be written as A minus B is equal to A intersection B dash. Or we can say that A minus B is A and not B. If PE is probability of an event, then P of E bar is probability of events other than the event E. Then probability of E bar is known as probability of the complementary event. We have an important relation. Probability of E is equal to 1 minus probability of E bar. The event E bar representing not E is called the complement of the event E. We can also say that E and E bar are complementary events. Let's take an example. Suppose we throw a die once. Then what is the probability of getting a number greater than 4? Let's see the solution. Probability of getting a number greater than 4 is total output events in the sample space is equal to 1, 2, 3, 4, 5 and 6. Number of events greater than 4 is 2, that is 5 and 6. Therefore, probability of getting 5 or 6 is equal to 2 by 6. That comes out to be equal to 1 by 3. Now, what is the probability of getting a number less than 4? Probability of getting a number less than or equal to 4. Probability of the complementary event, that is probability of E bar. So we can use the relation probability of E bar equals 1 minus probability of E. As we know, probability of E is equal to 1 by 3, as we had calculated just now. So, probability of E bar equals 1 minus 1 by 3, which is equal to 2 by 3. Let's take an example. Harpreet tosses 2 different coins simultaneously. What is the probability that he gets at least one head? Let's see the solution. Probability to get at least one head is when 2 coins are tossed simultaneously, the possible outcomes are H, 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 T, T, H, and T, T, which are all equally likely. You can see the 2 coins being tossed. The sample space is HH, HT, TH, and TT. Therefore, the number of all possible outcomes is equal to 4. Now, the number of outcome events having at least one head is HH, HT, TH, which is equal to 3. The number of outcomes favorable is equal to 3. Therefore, probability of E is equal to 3 by 4. Then the probability of no heads, that is only tails will come, is probability of E bar, that is equal to 1 minus PE, which comes out to be equal to 1 minus 3 by 4, that is equal to 1 by 4. Example. Consider the experiment of rolling a die. Let A be the event of getting a prime number. B be the event of getting an odd number. Write the sets representing the events 1. A or B, 2. A and B, 3. A but not B, 4. Not A. Let's see the solution. Here, the sample space denoted by S contains 1, 2, 3, 4, 5, and 6. The set A contains 2, 3, 5, and B contains 1, 3, 5. Obviously, A or B, that is A union B, equals to 1, 2, 3, 5. Number 2, A and B, that is A intersection B, contains 3, 5. Number 3, A but not B, that is A minus B, contains only 2. Similarly, number 4, not A, that is A dash, contains 1, 4, 6. Mutually exclusive events. In the experiment of rolling a die, a sample space S contains 1, 2, 3, 4, 5, and 6. Consider events A, an odd number appears, and B, an even number appears. We can see that there is no outcome which ensures the occurrence of the events A and B simultaneously. Here, A contains 1, 3, and 5, and B contains 2, 4, and 6. Clearly, A intersection B is a null set. That is, A and B are disjoint sets. Two events A and B are called mutually exclusive events if the occurrence of any one of them excludes the occurrence of the other event. Exhaustive events. Consider the experiment of throwing a die then the sample space contains the numbers 1, 2, 3, 4, 5 and 6. Let us define the following events. A, which contains a number less than 4. B, a number greater than 2 but less than 5 appears. And C, a number greater than 4 appears. Then A contains 1, 2 and 3. B contains 3 and 4. And C contains 5 and 6. We observe that A union B union C contains the whole sample space S. Such events A, B, C are called exhaustive events. In other words, events E1, E2 up to En are said to be exhaustive events if at least one of them necessarily occurs when the experiment is performed. Further, if Ei intersection Ej is equal to phi, for I not equals to j, that is, events Ei and Ej are pairwise disjoint, and we can say summation of Ei from I equals to 1 to n is the sample space. Then the events E1, E2 up to En are called mutually exclusive and exhaustive events. Let's take an example. 2 dice are thrown and the sum of the numbers which come up on the dice is noted. Let us consider the following events associated with this experiment. The sum is even. The sum is a multiple of 3. The sum is less than 4, or the sum is greater than 11. Which pairs of these events are mutually exclusive? Let's see the solution. There are 36 elements in the sample space. Then A contains the given elements, B contains the shown elements. Similarly, C and D, the elements which they contain are given. We find that A intersection B contains 1, 5, 2, 4, 3, 3, 4, 2, 5, 1 and 6, 6, which is not a null set. Therefore, A and B are not mutually exclusive events. Similarly, A intersection C, A intersection D, B intersection C and B intersection D, none of them are null sets. Thus, the pairs AC, AD, BC and BD are not mutually exclusive events. Also, C intersection D is a null set, and so C and D are mutually exclusive events. Example: a coin is tossed 3 times. Consider the following events. A. No head appears. B. Exactly 1 head appears. C. At least 2 head appears. Now, do they form a set of mutually exclusive and exhaustive events? Solution: the sample space of the experiment is S, which is shown, and A, B, C contain the elements which are displayed on the screen. Now A union B union C contains all the elements in the sample space, as you can see. Therefore, it is equal to S. Therefore, A, B, C are exhaustive events. Also, A intersection B, A intersection C and B intersection C are equal to null set. Therefore, the events are pairwise disjoint, that is, they are mutually exclusive. Hence, A, B and C form a set of mutually exclusive and exhaustive events.